Hi everyone, this is Marika Lamoureux, and this is a demonstration of how to hand calculate a one-way within subjects Anova. So at this point, you guys have already taken our first semester of Stats and Methods, and this is our second semester of Stats and Methods in the psychology major sequence. And a lot of you may be wondering why we require these two classes, especially considering many of you are not going to continue on to become psychology researchers. And this is a question that we get asked quite a lot, and I wanted to take one slide to perhaps explain it to you. So I hope this next slide gives you just a very brief understanding of why we feel it's important. So Neil deGrasse Tyson is a very famous physicist, and he oftentimes makes commentary about science education in America, and I thought that this was a very succinct way to explain why we feel it's important to educate all of our students about the science of psychology. Here's the problem we're going to use. I'll let you guys pause the video and read this, and when you're ready, unpause the video and we'll continue. Here's the data again, and of course we always have to start by stating our null and alternative hypotheses. So the null hypothesis states this is no different from a between subjects analysis, that there's no difference across conditions. And the alternative hypothesis, again, no difference between a within subjects design and a between subjects design. The alternative hypothesis says that there is going to be some difference across these three conditions. Here's our formula list. I'm going to assume that you don't need me to show you the formulas for all of the between subjects ANOVA stuff. When you're calculating within subjects ANOVA, you need to do all the steps for a between subjects ANOVA plus a few more steps to calculate this sum of squares people, sum of squares error stuff. If you feel like you need to review how to calculate all the between subject stuff, I encourage you to watch either of the two videos that I've already made on how to calculate a one-way between subjects ANOVA. So I'm going to talk a little bit about these formulas and explain how we kind of move from a between subjects ANOVA formula to within subjects ANOVA formula. Here's the formula for sum of squares between. It should look familiar to you. And the formula for sum of squares between is telling you how much of the variance in your sample is due to differences in the conditions. How is your treatment influencing your scores? And this is the fancy formula that some very smart people figured out to measure variance due to treatment. And if you look at the formula for sum of squares people, you'll notice that the formula is very, very similar. And this is on purpose, because those very, very smart people realized that they could use just a small variation of the formula for sum of squares between to figure out how much of the variance is due to people. So you can see that this formula is just summing across the scores for each person. And so sum of squares people tells you how much of the variance in your sample is due to just the fact that there are people that are the same people who are going across the different conditions. If you look at the formulas for an ANOVA for between subjects design and ANOVA for within subjects design, you can see that they're very different, and that they're very similar, and that the only difference is the denominator. So for a between subjects design, the denominator is mean square within, and for within subjects design, the denominator is mean square error. And you can see that's because in the sum of squares formula, we can subtract out variance due to people. And we can't do this for between subjects design because every single person in all of our conditions is different. So there's no variance that we can measure that's due to the person because everybody's different. But in a within subjects design, you have the same person across the different conditions, and so you can calculate how much variance is going on because of the people that you're using, and you can subtract that out. So when you are thinking of a formula as a measure of signal to noise, if the signal is how much variance is due to your treatments, and the noise is going to be how much variance is just due to random error. And when we're doing within subject design, we can subtract out from that error formula how much variance is due to the people. So this is really nice because we are going to shrink the noise part of the signal to noise equation, and we're going to make it more likely, usually, that you'll find a significant effect if you're looking at it within subjects ANOVA than a between subjects ANOVA, because you've shrunk your noise. Okay, so here are the formulas again, and you can see that there's the formula for sum of squares people and for sum of squares error, and the formula for an ANOVA. And you can see how we're taking advantage of the fact that we can calculate the variance due to people and subtracting that out of the error that we would be looking at in the ANOVA. Again, I'm going to assume that you can calculate all the between subjects stuff. And so here are the values that you would have calculated. And now we need to calculate sum of squares people. So the P stands for each person's total. So it looks like this for our sample. And so you're looking at the total for Shakaya squared over the number of levels plus the total for Isabel squared over the number of levels, so on and so forth, minus the total for all the scores squared over the total number of scores. And I've gone ahead and put it in a table format because I always think it's much easier to keep your notes very clear, and so this way it's very clear what the p-values are for each participant. And this is what the formula ends up looking like for this data set. So now that we have sum of squares people, we can go ahead and calculate sum of squares error, mean square, ANOVA, the F value, and our eta squared. And eta squared is the same for between subject design and a within subject design. So here are all the things that we already know. So our sum of squares error is going to be 26.34 minus 19.78, which equals 6.56. Our degrees of freedom error is going to be 18 minus 3 minus 6 minus 1, which equals 10. And if we know our sum of squares error and our degrees of freedom error, we can calculate our mean square error, because mean square is always equal to sum of squares divided by degrees of freedom. So that equals 0.66 for this data set. And if we know our mean square error, we can calculate our F value, because F is mean square between over mean square error. And for this data set, that equals 11.20. And we can also calculate our eta squared. And for this data set, our eta squared equals 0.36. Now we go to our friendly F table, and we know our degrees of freedom between and our degrees of freedom error. And you might be saying to yourself, oh, now I understand why the table is in terms of numerator and denominator, because what the denominator is changes whether it's a within subject design or between subject design. So we're doing a within subject design, and we're going to be using this formula. Mean square error is our denominator. So we're going to use the values of 2 for the numerator and 10 for the denominator. So we have 2 in the numerator, 10 in the denominator. And when you put your fingers together and see where they meet up, that comes up with an F critical value of 4.10. So we know our F crit and our F calc, and we can see that our F critical value is smaller than our F calculated value. So we're rejecting our null and supporting the alternative hypothesis. And we can see that our alternative hypothesis is that there is some difference in how people drive under control conditions while speeding or while texting. So the way that you write this up for within subjects ANOVA is identical to the way that you would write it up for between subjects ANOVA. And you're going to use what you already know to write a sentence to say, there is a difference in how many errors people make when driving under control conditions, speeding, and texting. And again, you can't say, just on the basis of these tests that we've done, where the difference lies. So you may want to look at the data and sort of say like, oh, well, this mean looks bigger than this mean, so I think this is where there's a difference. But with an ANOVA, you have to do post hoc tests in order to tell what the differences between conditions, which between condition differences are significant. And this video does not cover how to do post hoc tests. And that is how you calculate a one-way within subjects ANOVA.